Have you ever, been staring at a really tough piece of metal, maybe doing some DIY, or wondered how those massive steel plates in a shipyard get shaped so precisely? Well, it's rarely about just brute force. Often it's about harnessing some serious heat. Today, we're taking a deep dive into thermal cutting processes. We're going to explore how we actually slice and remove metal using intense heat, and it happens in some surprisingly different and specialized ways. We've pulled together some expert materials on these processes, aiming to give you a real shortcut to understanding this, well, pretty essential part of metal fabrication. Our mission for you today is to get a handle on the core principles, the distinct advantages, and the key limitations of the most common thermal cutting methods. By the end, you should be able to recognize which process fits which job, which material, and really appreciate this fiery, precise world. So let's ignite the conversation.
Right. Let's kick things off with the undisputed classic, Oxy-Fuel cutting. Now, the fundamental principle here, it isn't just melting the metal. What's really fascinating, I think, is that it's actually a controlled chemical reaction. You start by preheating the metal with a gas flame that's a specific mix of fuel gas and oxygen until it hits its ignition temperature or burning temperature. We're talking around 850 degrees Celsius. Once you hit that critical point, a separate stream of incredibly pure oxygen, like 99.5% pure or even higher, is directed onto the hot spot. This pure oxygen then rapidly oxidizes the hot metal. It basically burns it away, and the kinetic energy from that oxygen jet blasts away the metal oxides and any molten metal. As the torch moves, you get that continuous cut. It's pretty neat when it works well.
Okay, that really clarifies it. So it's not just melting like a candle, it's a controlled burning process.
Yeah.
Very specific. So what kind of metals actually, play ball with these conditions?
That's the million-dollar question, right? For Oxy-Fuel cutting to actually work properly, two conditions absolutely have to be met. First, the metal's burning temperature has to be lower than its melting point. That's crucial. And second, the melting temperature of the oxides that form during the cutting, well, that also needs to be below the parent metal's melting point. Because of these really specific requirements, the process is pretty much limited to carbon steels and some low alloy steels.
Okay. So what happens when you try it on other stuff like stainless steel or aluminum?
Yeah, that's where you run into trouble. The challenge comes with certain alloying elements, like aluminum and chromium, which you find in stainless steels. Their oxides actually have melting points that are higher than iron oxides. We call these refractory oxides. And they basically form a shield, They protect the underlying metal, stopping fresh iron from getting exposed to that cutting oxygen stream.
So it just stops or gets messy.
Exactly. It slows the cut right down or makes the whole process unstable, sometimes stopping it completely. So in practice, you're looking at low alloy steels with really low percentages of these elements. We're talking less than about 0.25% carbon, less than 5% chromium, maybe less than 5% molybdenum, stuff like that. If you have to cut high alloy steels or cast irons, you need special tricks, like adding iron powder or flux into the flame to kind of help the reaction along. Otherwise, it just won't cut properly.
Right. So it sounds powerful for the right job, but definitely picky about its materials. So thinking practically for someone in a fab shop, what are the big advantages that make Oxy-Fuel the go-to sometimes? And where does it really fall short?
Well, the advantages are pretty significant in its sweet spot. For steels, it's generally much faster cutting than most machining methods, especially on thicker plates. It's really economical for cutting complex shapes or very thick sections that would be super difficult or maybe even impossible to do mechanically. And the basic equipment, it's relatively low cost compared to big machine tools. Plus, the manual gear is highly portable. You can easily take it out on site.
That portability seems like a huge plus for field work.
Absolutely. And you can change direction quickly, tight corners, no problem. You can cut huge plates just by moving the torch, not the plate. It saves a ton of handling. And it's great for prepping plate edges for welding. Very economical for that.
Okay, sounds good. But what about the downsides, the trade-offs?
Right, there are definitely trade-offs. Dimensional tolerances, well, they're significantly poorer than what you'd get from machining. Don't expect laser precision here. And as we've said, the material limitation is a big one, basically, carbon and low alloy steels. Safety is a major consideration, too. You've got an open flame, you've got red-hot slag being ejected, serious fire and burn risks.
Yeah, you definitely need proper PPE and setup for that.
Definitely. And fume control is crucial. You're burning fuel, oxidizing metal. You need good ventilation.
Mm-hmm.
Also, for some steels, the ones that can harden easily, you might need to preheat or post-heat the cut area to control the metal structure, avoid making it brittle right next to the cut. And like any hot process, you've got expansion and shrinkage. You have to account for how the part might warp or distort from the heat. It needs managing.
It really paints a clear picture of the pros and cons, doesn't it? Great for some things, like heavy steel, on-site work, but not for high precision or tricky alloys.
You mentioned oxygen purity earlier being really critical. Can you expand on that? And what about the different fuel gases? Because that preheating flame sounds like it's doing more than just heating things up.
You are absolutely spot on. Oxygen purity is paramount. For cutting, it has to be 99.5% or higher, period. If it drops even just a bit, say below 95%, you see a massive drop in cutting speed and a huge jump in how much oxygen you use. It just kills the efficiency. Below that 95% threshold, it basically stops being a clean cut and turns into what we call melt and wash. The oxygen just kind of melts the metal and pushes it away. Very poor edge quality, generally unacceptable.
Okay, so 99.5 or bust. Got it. And the preheating flame. Yeah, it's a real multitasker. So obviously it gets the steel up to ignition temperature. That's job one. But it also keeps adding heat energy to maintain that cutting reaction as you move along. And importantly, it acts like a protective shield between the pure cutting oxygen stream and the surrounding air. Stops things getting contaminated. Plus, it helps to dislodge surface stuff like rust or scale or even paint ahead of the cut.
Interesting. So choosing the fuel gas for that preheat flame, what goes into that decision?
Good question. You're balancing a few things. How fast does it preheat? That affects your start time, especially for piercing. How does it impact cutting speed and productivity overall? Then there's cost and availability, obviously. How much oxygen does that specific fuel need for the preheat? And, of course, safety considerations for handling each gas.
So different gases for different jobs.
Exactly. Take acetylene. It gives you a very hot, very focused flame. That means super quick preheating and piercing. And it actually needs less oxygen for that initial preheat compared to others. So it's really good for thinner plates doing bevel cuts or jobs with lots of shortcuts or multiple pierces.
Okay, and what about something like propane?
Propane's different, lower flame temperature, but it has a higher overall heat content. So it's slower to preheat and pierce, and it needs more oxygen for the preheat part. But that sustained heat makes it excellent for cutting thicker sections, say 100 to 300 millimeters thick, and for long, continuous cuts where you just keep going. There are others too, like MAPP gas, which you sometimes see used for specialized things like underwater cutting.
Right. And what does a typical Oxy-Fuel cut actually look like in terms of quality? What are the characteristics?
Yeah. Typically, you get a fairly wide cut, the kerf we call it, usually over 2 millimeters. The surface roughness can actually be quite low, maybe less than 50 micrometers raw, so it feels smoothish. But the edge squareness isn't perfect. You might get deviations over 0.7 millimeters. And you'll definitely see a heat-affected zone, the HAZ, that's usually over a millimeter wide, where the metal properties have changed.
So what's a good cut look like then, if you nail the parameters?
A satisfactory cut, yeah. You want a sharp top edge, nice fine, even drag lines, those little vertical grooves on the cut face, very little oxide buildup, a sharp bottom edge, and ideally no slag sticking to the underside. That's the goal.
Okay, this is gold for anyone actually doing this.
Yeah.
How do you spot trouble? What are the visual cues if you've got your settings wrong? Like if you're going too slow or too fast?
Reading the cut, that's the real skill. It tells you everything. If you're cutting too slow, the top edge will look melted over, rounded. You'll see really deep grooves down the cut face, heavy scaling, and a rough bottom edge with lots of sticky dross that's hard to chip off.
Okay, melted top edge, deep grooves, too slow. What about too fast?
Too fast. The cut edge becomes irregular, kind of wavy. Those drag lines will be coarse and noticeably angled, not vertical. Again, you'll get excessive slag really sticking to the bottom edge.
Gotcha. What else? Flame settings.
Yep. If your preheating flame is too low, you often see deep gouges just in the lower part of the cut face. The cutting oxygen isn't getting enough thermal support down there. Conversely, preheat flame too high, you get that melted top edge again in a regular cut, and yeah, excess sticky dross.
And even the torch height matters.
Oh, absolutely. If the nozzle, the blowpipe, is too high above the plate, you'll see excessive melting right on that top edge, and probably a lot more oxide buildup on the face. And finally, if your travel speed is jumpy, not smooth and consistent, the spacing of those drag lines will be uneven, the bottom surface will look irregular, and you'll get patchy bits of oxide stuck on. Each sign points to a specific adjustment.
That's incredibly useful, like a troubleshooting guide written right onto the metal itself. Okay, so Oxy-Fuel is great for certain steels, but has its limits. What happens when you need to cut those other metals or need more speed? That's where we pivot to plasma arc cutting, right? Turning up the heat electrically.
Plasma arc cutting, or PAC, it uses a constricted electric arc and a high-velocity jet of ionized gas, that's the plasma, to basically melt and blow away the metal. In the most common setup, the transferred arc method, you strike an arc between a tungsten electrode inside the torch and the workpiece itself, which has to be conductive. Gas, often just compressed air, but sometimes argon or nitrogen mixes, flows through this incredibly intense arc. We're talking temperatures in the tens of thousands of degrees Celsius. Hot.
Wow.
This superheated gas expands massively and then gets forced through a tiny constricting orifice or nozzle. This accelerates it into a very high-velocity plasma jet. This jet hits the workpiece, melts the metal almost instantly, and the sheer force of the jet blasts the molten material out of the cut path. There's also a non-transferred arc version where the arc stays inside the torch, used for cutting non-conductive things, but that's less common for metals.
That sounds incredibly powerful and way more versatile if it's not relying on that specific chemical reaction.
Yeah.
So what are the big advantages and the things to watch out for with plasma?
Versatility is definitely a huge plus. Unlike Oxy-Fuel, it's not limited to just ferrous metals that meet those strict oxide criteria. It works brilliantly on all types of stainless steels, aluminum, copper, brass, pretty much any conductive metal.
And even non-conductive with that other method.
With the non-transferred arc, yes, though less common. The main thing for metals is it operates at a much higher energy density than Oxy-Fuel. This translates directly to much faster cutting speeds, often several times faster, especially as the material gets thicker. Plus, it's instant startup, no preheating needed. Flick the switch, strike the arc, and you're cutting. That's a massive advantage for interrupted cuts or jobs with lots of piercing.
Faster, more versatile, instant start. Sounds great. What are the catches?
Well, like Oxy-Fuel, the dimensional tolerances are still generally poorer than what you'd get with precision machining. It's a thermal process, so expect some limitations there. And the hazards are significant. You still have fire risk from sparks and molten metal, but now you add electrical hazards, high open circuit voltages needed to strike the arc. There's also intense UV light from the arc, requires serious eye and skin protection. Significant fumes and gases are generated, and it can be loud.
Okay, so safety is a big factor. Noise, fumes, UV, shock risk.
Definitely. Although cutting underwater, which is sometimes done with plasma, actually helps mitigate the fumes, UV exposure, and noise quite a bit. But that's a specialized setup. Also, the equipment is generally more expensive than a basic Oxy-Fuel setup, and it needs a hefty electrical power supply. Again, being thermal, you have to consider expansion, shrinkage, potential distortion. Oh, and the cut edges can sometimes have a slight taper to them.
Right, so more upfront cost, more power needed, and a different set of significant hazards to manage.
So when does it make sense to choose plasma over Oxy-Fuel, giving those points? What's the real decider? It really comes down to the material you're cutting and the speed you need. If you absolutely have to cut stainless steel or aluminum or copper alloys efficiently, materials that Oxy-Fuel just can't handle well or at all, then plasma is the obvious choice. It opens up that whole range of materials. And even on mild steel, where Oxy-Fuel could work, if you need significantly higher cutting speeds, maybe for production volume on thicker sections, the speed advantage of plasma can make it much more economical overall, despite the higher initial cost. It's about broadening capabilities and boosting throughput.
That makes perfect sense. Matching the process to the material and the production needs. Okay, so we've cut through things. Let's shift gears slightly to a process that's more about removing metal, maybe not cutting all the way through. Arc gouging. Tell us about arc air gouging first. What's happening there?
Right, arc air gouging. It's a really effective way to melt metal using an electric arc, and then use a high-velocity jet of compressed air to blow that molten metal away. You use a special torch that holds an electrode and has air passages built in. It connects to a standard arc welding power source, like for stick welding, and also to a compressed air line. You need a decent amount of air, usually around 100 psi or 690 kPa. Interestingly, you often don't need a precise regulator for the air. The electrode itself is typically made of graphite, often coated with copper, to help with electrical conductivity and make it last a bit longer.
And what's it mainly used for? Not cutting plates in half, presumably.
No, exactly. It's primarily for gouging, creating grooves or channels in the metal. Think about removing weld defects, back gouging welds to ensure full penetration, or creating specific edge preparations for welding, like U-grooves or J-grooves. And a key point is, like plasma to some extent, it works on both ferrous metals, like steels and cast irons, and non-ferrous metals.
Okay, so removing material fast, what are the big advantages?
Speed is definitely one. It's roughly 5 times faster than trying to remove the same amount of metal by chipping with a chisel. It's also very controllable. Because you can clearly see the molten pool and the defect you're chasing, the operator can follow it easily. You can regulate the depth of the gouge quite nicely, and unlike chipping, slag doesn't really deflect the gouging action. Equipment cost is relatively low if you already have a suitable welding power source. You don't need expensive gas cylinders or regulators like with Oxy-Fuel, unless maybe you're working remotely.
So fairly economical to run, too.
Yeah, no oxygen or fuel gas costs, and a welder can usually pick it up pretty quickly. The skill set is similar to stick welding, often no extra qualification needed just for gouging. The equipment's easy to operate, the torch is fairly compact so you can get into tighter spots, and it's versatile. You can even automate it for repetitive jobs.
Sounds pretty useful. Downsides?
Well, while it's great for gouging, if you actually want to cut through a piece of metal, other processes like Oxy-Fuel or plasma are usually better and faster for that specific task. It does need a lot of compressed air, so you need a compressor that can keep up with the volume. A big one, metallurgically speaking, is that the process can actually increase the carbon content right on the surface of the gouged area. This can lead to increased hardness, especially in cast irons or hardenable stales, which might be undesirable.
And what about stainless steel? You mentioned issues with other processes.
Yes, for stainless steels, that potential carbon pickup can lead to something called sensitization. The extra carbon combines with chromium near the grain boundaries, depleting the chromium locally and making those areas more prone to corrosion later on. So after air gouging stainless, it's pretty much mandatory to grind away that thin surface layer to remove the potentially sensitized material and restore the corrosion resistance.
Right, grinding is key for stainless and other hazards, similar to plasma.
Similar, yes. You've got the arc. So intense, light, proper shielding needed, lots of sparks and molten metal being blown around, so a definite fire hazard. Significant fumes are generated, and it can be quite noisy. So good PCE and ventilation are absolutely essential.
Okay, so definitely a powerful tool for specific prep and repair tasks, but with those metallurgical points and hazards to keep firmly in mind. Any other key operational details someone using this needs to know?
Yeah, a couple of crucial ones. Arc air gouging operates only on direct current electrode positive, or DCEP. That polarity focuses the heat correctly for efficient melting at the electrode tip. You absolutely need a clean, dry, compressed air supply. Any moisture or oil in the air can cause arc instability and poor results. And just to reiterate, especially for hardenable steels or stainless steels, grinding that potentially carburized or sensitized layer after gouging is really important for the final quality and integrity of the part.
Got it. DCEP, clean air, and grind afterwards, especially on sensitive materials. Now, you also mentioned manual metal arc gouging. Sounds like using a regular stick welder, but for gouging. How does that work and compare?
Right. Manual metal arc, or MMA gouging, sometimes called stick gouging. It is related but distinct. You use a standard MMA-stick welding power source, but with special gouging electrodes. These electrodes have a very thick flux coating compared to welding rods. When the arc burns, this thick coating generates a really strong arc force and a large volume of gas. Unlike welding, where you want a stable pool, here the idea is that the forceful arc and the gas blast physically push the molten metal away from the arc zone, leaving a groove or gouge behind. So it's all about generating enough force and gas to eject the molten metal.
Okay, so it uses the electrode itself to create the blast, no separate airline. How does it stack up against the arc air method then?
Well, the main difference is that the arc force and gas stream from just the electrode coating, while strong, are generally not as powerful or focused as that dedicated jet of compressed air in the arc air process. This usually means the resulting gouged surface isn't as smooth or clean. You tend to get a rougher finish compared to arc air or even Oxy-Fuel gouging. Also, the metal removal rates are typically lower, it's just not as aggressive, and the overall quality of the surface left behind is generally considered inferior to the alternatives.
So why use it then, if it's rougher and slower?
Convenience, mostly. It's good for very localized gouging, maybe removing a small surface defect, or situations where an operator is already stick welding, and it's just much easier to switch to a gouging electrode for a quick removal task rather than setting up the whole arc, air torch, and air line. It's about having a quick option with the gear you already have out.
Makes sense. And the carbon pickup issue, still relevant here.
Yes, absolutely. Just like with arc air gouging, particularly on stainless steel, MMA gouging will produce a thin surface layer with potentially higher carbon content. So again, if the material properties or corrosion resistance are critical, that layer really should be removed by grinding afterwards.
Wow, okay. We've really journeyed through some intense heat today, from controlled chemical burns slicing through steel to that superheated plasma tackling almost anything conductive, and then these focused arc methods for gouging and removal. So just to recap quickly, we saw Oxy-Fuel, the classic, relying on that chemical reaction, great for certain steels, economical, portable for site work. Then plasma, using the electric arc, much higher energy, way faster, handles a huge range of materials, conductors, and even non-conductors potentially.
Right, speed and versatility are key there.
And finally, arc gouging, both arc air with the air blast and MMA with the special electrode. Not really for cutting through, but for precision removal, prepping edges, fixing defects.
Exactly. Each one really is a distinct tool. If you try and connect it to the bigger picture, you see they're definitely not interchangeable. Each has its specific niche, its best fit application, and its own unique set of trade-offs. Could be precision, could be portability, material compatibility, or just the plain old cost of the equipment and running it. Understanding those differences, those nuances, that's absolutely vital for picking the right process for whatever job you're facing. It's all about efficiency and getting the quality you need.
Couldn't agree more. The best method really does depend entirely on that whole mix. The material, the cut quality you need, how fast you need to do it, and all those equipment and safety factors. So thinking ahead then, considering the amazing precision and automation we're seeing, especially with things like robotic plasma and Oxy-Fuel cutting, what new challenges might be coming down the pipeline, like with emerging materials, maybe advanced composites or parts made through additive manufacturing with their complex internal structures? How might these thermal processes we've talked about today need to adapt or evolve to handle those future cutting challenges? Something to think about. Well, thank you for joining us on this deep dive into the pretty fiery and fascinating world of thermal cutting processes. We hope you feel a little more informed, maybe just a bit more curious about how things are shaped and made. Until next time.